Hello, my name is Ariff Kenichi, bin Ahmad Zaki Akira, matrix number 1913925542, program RY41. In this video, I will present about the online assessment 1 for the PGT213 analog electronic 2. So, what is an OPM and what is the ideal characteristic of the ideal OPM? So, there's several parameters we need to keep in mind. There's several more, but I take a few of them. So first, the input current. For the ideal OPM, the input current, we want it to be 0. The input offset voltage, also 0. The input impedance is infinite. Output impedance is 0 ohm. The voltage gain uh, is 0 and the bandwidth, the voltage gain is infinite and the bandwidth is also infinite. So for the input impedance is infinite, we can also say it's an open circuit. Okay, distinguish the properties between the LM740 and the ideal OPM. So by comparing the ideal and the practical, so practically we want it as close as an ideal OPM. So for example, the input current, we want it to be 0. So that means we want it as low as possible. So input current low, input offset voltage is also low. The input impedance as high as possible. Output impedance as low as possible. The voltage gain and the bandwidth as high as possible for the practical. So there's several values I add in here. I have taken from the data sheet. So basically it's almost similar to the ideal. Now we continue with the second question. If the OPM were perfect, the ideal step response of OPM we produce. In practical, however, the output is exponential with a certain time interval. So show an OPM with the input step and its resulting output of the slew rate. So in ideal situation, the input we produce a square wave and the output for the slew rate is gonna be slightly slew from the square wave. So we only gonna take 10% to 90% of the total output waveform. So in this case, I will show the with the value. So for example, the V out is 10 volt peak. So the slew rate is the difference of voltage output over the difference of time. So in this case, it's 9 volt minus with negative 9 volt over 1 microsecond. So in this case, we're gonna get 18 volt per microsecond. So what is slew rate and is it important? So slew rate can be defined as the maximum rate of change of an OPM's output voltage. So practically, we're gonna take 10% to 90% of the output signal's amplitude. So is it important? Basically, yes. It's important to identify the maximum input frequency and amplitude where the output is not significantly distorted. And slew rate is important to ensure the circuit is accommodate fast output rises and reduce distortion. So to show that it's important where slew rate is being used in several cases where it's used in musical instrument such as portamento or we can call it glide and used in the slew circuitry where it's control the voltage over a period of time, either gonna make it fast, the changing fast over time or slow. Next, we continue to question number 3. Give an example of an inverting amplifier using an OPM with the component value and explain. So I've done an experiment where the V input is 1 V peak, 1 volt peak, and the R in or R1 is 1 kilo ohm and RF is 10 kilo ohm. So the first A, where is the virtual ground? The virtual ground is located there. How do I know? Is the several properties for a virtual ground, where the input, uh, we can determine the virtual ground location where the non-inverting has been grounded. So the inverting terminal have a zero voltage. So in this case, when it's virtual ground is at the center there, the node over there, there's no current at inverting. We can say that the current in the input current is equals to the IF. So from the experiment that I did, here's some theoretical calculation. So IN is equals to IF. So using the Ohm's law, so V equals to IR. So we finding the IN. So V I V in is over R in. So in this case is 2 divided by 1 kilo. We can get is 2 milliampere. So from the equation, I in is equals to IF. So IF is also 2 milli. The input impedance is approximate to R in. So in this case is almost the same as R1 here. So it's 1 kilo ohm. So next is V out. To calculate the V out. So the formula is negative I in times with R in. So negative 2 milli times with 10 kilo, you can get negative 20 volt. So for the gain or closed loop gain is negative RF divided by R in. So 10k divided by 1k with the negative in the front, so we can get negative 10. We can check the voltage output with using the ACL. So V out is equals to the gain times with voltage input. So negative 10 times with the 2 volt equals negative 20, which is similar. So the theoretical we are going to compare with the experimental value. The current for the experiment and the calculation I get the same, but the voltage output I get slightly different by 0.1 volt, but it's okay, I mean it's acceptable. So finally, the question 4, construct a summing amplifier and summarize the theory. So this, I'm going to talk about the theory first. So summing amplifier have multiple inputs where the Zin is infinite. Uh, the virtual ground is located at this node because it's an what's called it's an inverting amplifier. It's almost similar to inverting amplifier where the non-inverting is grounded. So from here we can know that the IF flow here is equals to the total of I input. So I1, I2, I3 and so on. So from here, if we want to find the V out, so using the Ohm's law, V out equals to IR. So in this case, we put negative since it's moving in opposite direction. So it's IF equals to I1, the total of I, and then we substitute. So I equals to V over R, and then we substitute, we expand the equation. So in this case, for example, we have this value. So input 1 is 4 volt, 2 volt for input 2, 3 volt, and finally is 6 volt. So R1 is 50k, R2 100k, R3 is 20k, and the RF is 20k. So from this experiment that I done, I get the output voltage is negative 8.195. So to prove that it's similar, so by using the formula previously, theoretical formula, so we substitute all the values into the formula and we can get negative 8.2, which is almost similar do the the simulation. And that's all from me. Thank you.